Hello everyone, and thank you for joining us today. Welcome to Megger's Monthly Tasking Tactics webinar series. Today's topic is Fundamentals of Generator Protection Testing. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NIDA CTD and one PDH or zero point 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is David Beard, TSG Applications Engineer. Also to assist with the question and answer session, we have 2 panelists joining us today. We have Abel Gonzalez, Senior Applications Engineer, and Dana Bomani, Senior Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, David.
Okay, welcome everybody. Today we will be talking about fundamentals of generator protection and a little bit of testing techniques into this. So thank you all for showing up and attending the webinar session. Today we will go over a little bit of an overview of how the generators work. We'll also go over, in generator protection, we'll do differentials. We'll look at 100% stator ground, loss of field, inadvertent energization, reverse power. The little bit of testing tips will, at the end of the session, we'll actually show differential testing example, and we'll actually go through a little bit of talking through that, and then we'll also conclude with a summary. So the big question always is how do we get electricity? For those that are in the industry, we do understand and we do know, but we'll just kind of go over a little bit of a basic overview. Since power lines run through the landscape and through our cities, we're actually, the power grid, we actually come from the generator side, coming into the transformer and then come down to where we can use the consumable power. We can consume the power that we're actually using for all of our powering our electronics and so forth. But the big question is how do we actually get this power, and how is this power actually generated? Well, it all started with this gentleman here, Michael Faraday. So a little bit of a history. He was a British chemist and a physicist, and he worked in the field of electromagnetism and electrochemistry. So he produced, or actually invented a few, benzene, I believe, was the chemical that he actually founded, and also he worked in trying to produce mechanical motion. In 1821, the motion he created was by this diagram here, which you can see is the coils that he wrapped around some iron and actually was moving the coil back and forth to see this galvanometer move in both directions. 10 years later, he actually was able to convert the magnetic force into electrical force, inventing the first electrical generator. The style of cylindrical rotor that you see here is common. It's the most common that you see for steam turbine generators, gas turbine generators. Doesn't have a large amount of poles to it, usually ranging between 2 to 6, depending on the application. They're very small in diameter, and they're used for higher speeds, up in the range of higher than 1,000 RPMs. This type of cylindrical rotor does not need dampener windings, and is usually found in the gas and steam turbines. As you can see, that you'll find the small little equation that you see here, you can plug in a few values and you can actually get the frequency that you want to output depending upon the size and the style of the different rotors. The salient style rotor is very large. It's large in diameter, but it's very short. And most of the time you see these in hydro plants. And then also they rotate at a lower frequency, they have lower RPM range, given them that they have multiple poles for the actual generator itself. They're actually spinning at a slower speed to be able to produce the same frequency, 50 or 60 hertz, as the cylindrical style rotor. So how's AC generated? So what you do is you're going to have a prime mover, and the prime mover is going to be the mechanical energy that you're actually going to use to create electrical energy. So you will go through, and there will actually be some prime movers are powered by natural gas. They're powered by steam or even by diesel engine. And as this prime mover is actually rotating, we're actually generating. We're not generating electricity yet. We also have to have an exciter. So what the exciter does is the exciter takes the rotor windings and puts a DC source across the rotor winding to give it a north and a south pole. As the rotator is rotating around inside the generator, the stator wings are actually getting the induced current that's actually going to be put out into three-phase power. Now doing this process, there's a lot more parts and pieces that go into this, but for our general purposes, we just want to know the actual concept of what we're trying to accomplish. In the protection world, we're wanting to know the reason why we're actually generating AC, how it's working, and also how we're able to better identify and understand the elements that are in generator protection. So in this diagram, it's a little bit of a different way to look at it. So what we do is we will follow this diagram here. We have three-phase power, as you can notice by the sine waves here in this area. And we have the rotor style in the middle with the actual different pole windings on the outside that are placed within the generator itself. Now, as this rotation happens, we will follow this red, or A phase we can call it today, line. So as we'll say, this is North Pole, and then this will be the South Pole, and it will be positive or negative from the DC source that's coming into the rotor. So as this rotor is spinning, you will notice that now we are perpendicular to the red winding, the red stator winding here, right? As you can see on both sides. So this pole will actually show, since we're perpendicular, no electrons are moving into the stator winding, so therefore we are at zero. As this rotation happens, it'll come up to the 15 degree as we're rotating counterclockwise. Then you'll notice that we're inducing a little bit of voltage here. So we're seeing the electrons are flowing in the positive direction. So as we continue to move all the way around, if we move even to the 45-degree angle, you'll notice that we're going to see, so we're got a little bit more induced voltage here at the 45-degree angle on this red phase, or A phase as we call it. As you get to 90 degrees, the actual North Pole, or which will be our positive pole, is actually touching the stator winding. It's not touching it, it's rotating closest to it. It's at our peak value. So at the peak value, that the most flux lines that are being cut to allow the highest induced voltage here, where you're going to see the peak at the top. And then as we rotate farther around to 120 degrees, you're going to actually see this is starting to come down off of the peak side and start to come down to the negative end of the other end of the sine wave. So as we rotate all the way around, we'll get to the 150 side. The 150 is going to come around, as you can tell that we're actually seeing it here. It's coming down. And then as we rotate all the way back around, then we will be at the peak of the negative side of the sine wave. And the negative side of the sine wave will be here at the 270 mark. as you can see on the graph. And as this guy is as the rotor is rotating all the way around, you'll notice that each phase is going to start at a different time as well. So we have the 3 poles will start at different times. Not every pole will start at 0 according to this drawing here, where this is just showing us from where we're starting at A phase. But as A phase is starting, you will notice that we would say even C phase, B phase, and C phase here. C phase has already got some induced current coming into this guy inside this phase and is inside the stator winding here. So as it's rotating around, we're getting a 3-phase sine wave that's continually moving. There are many different types of faults that can happen within this generator system, and there can also be faults in the stator and the rotor as well. And these could be, the stator overload. We're overloading the stator windings. We're over-exciting the rotor. We also have the winding faults, so there can be the phase to ground faults in the stator. There can be phase to ground faults in a rotor, or shorted turns in the windings. And of course, there's abnormal running conditions, which could be, over and under speed, over voltage, unbalance, failure of the prime mover, which means that we could actually have lost steam, could have lost a gas line, we could have lost any type of the mechanical energy that will be used to actually move the prime mover. And then also we could have lost the excitation system. So we could have actually lost the DC source, the DC side of the rotor to actually produce the power. This here is just a quick overview to kind of let you look at what protection is encompassed into a full generator package. Now this with being the generator's unit connected to the transformer, you'll notice that there's multiple relay elements that are used. There's lots of overlap as far as protection is concerned. And 2, we want to make sure that we don't leave any piece of any wire, any breaker, any device inside of this the protection of it, the actual circuit, the actual generation circuit, unprotected. Today, what we're going to be talking about will be the differential. It's the ones that I have highlighted in red, and of course, the rest of the IEEE elements here. We will go over the stator, 100% stator ground. We won't really be talking about the 64 element that much, but the idea and the concepts we can get from the 59 and the 27 element as well. Okay, differential protection. Okay, here's an example of a differential scheme, and we'll just kind of walk through it briefly. So as we're going to have a normal scenario, as we are generating power through the generator here, we're actually seeing the flow of the CTs, the current that's flowing into the CT, and you'll notice that the CT here, this is coming out of the generator, will actually flow into the relay differential circuit and then come around as this circuit is made, I should say. As the current comes to the unit and comes back, then we're actually flowing through the actual CT here, and then you'll see the same amount of current that's coming across the relay as well. Now these two currents that are coming into this CT is actually going to equal to 0. With the current in here, it's going to be I1 minus I2 will be 0 across this relay, so therefore everything will look proper, everything will function properly, and everything is good. When we do have a fault into the relay, an internal fault, and the relay sees it, then this generator is actually going to be feeding into this fault. And when the generator feeds into the fault, then we will get a reverse from the current coming back from the transformer or the unit or the breaker transformer combination that's over here back into the system. Now, this usually happens when we have this unit is connected to the system. And then also if we just have a fault here and we don't have this unit connected to the system and we open up, then we would also get a difference from one side generating current and the other side not seeing this current here. So there can be a difference in two different ways, but we will actually add the two currents across this relay, across its operating coil, and then we will actually get a difference. So what we're looking for here is we want to make sure that what current equals what current going out equals what current is actually going in. And that's it. Anytime we have a difference in those two currents, then that's when our relay is set to pick up and trip. So in the differential protection, what are we actually looking for? So the purpose is that we're trying to protect against internal generator faults, right? Or inside the protected zone of the CTs. So if our CTs are wrapping some other type of device, we're still wanting to protect within the CT zone. We also have an example of a few relays, you know, an old CFDs. These are electromechanical style relays here. With the old CAs are usually pretty popular. The ABB circuit shields are little solid state relays. There's not too many of those out. And then Bassler makes a relay as well. And then any microprocessor based relay that has any type of 87 elements that can be used, 87G, 87GD, 87 TD for wrapping the generator or any type of other protected device outside. When we test, what we're trying to do is we need to make sure that we have at least a minimum of two currents. Because we want to be able to test on both sides of the winding. On if we have two different windings in a relay, we want to test winding 1 against winding 2 on the same phase. It would be very good to test 3-phase. That way you can get your just like it is in the system, you want to make sure that you can actually push in 3-phase current on both ends, and then also do your faults in the same manner. And then also we want to pick up on each winding just to make sure that our settings are valid. Want to make sure that everything is calculating out properly. And 2, whenever we're building test plans, we also want to make sure that we are bringing in the correct values. So it just kind of gives us a little bit of an extra step there, but we also want to check the pickup on the windings. The slope test. Now we didn't talk too much on the slope test for this, but what we're doing with the slope test is we are wanting to make sure that the if it's enabled for the generator, sometimes you have that the CTs on both sides of the generator are actually going to be pretty close to the same make and model, but they still have some inherent flaws, some errors in the CTs, the ways that they're actually manufactured. You could have a little bit of a deviation in the phase angle of the CT. You could have a little deviation in just the errors and the ratios and so forth, and CT saturation. So what ends up happening is that we want to check a slope. So if engineering department decides to put in a slope characteristic for this relay or this type of protection scheme, then what we'll do is we'll need to check that as well. Whenever we do that, I'll kind of explain it a little bit in the next couple of slides. We actually have a pretty good drawing for that. When we are doing the test, we want to make sure that our actual fault tests that we're 100 degrees out of phase. And then also, if there's some type of microprocessor relays will actually, sometimes if you're wrapping the transformer with the generator protection, then you might need some type of CT compensation for the different type of transformer that you have. If it's a delta Y, delta Y1, delta Y5, you kind of need some compensation there from the way that the actual transformer is being wound. Here's an example of the test. what the test would look like, we actually, to do the pickups on the windings, you can come in with the actual setting. This will be a per unit setting calculated from the actual values of what the generator, MVA of the transform of the generator, and also the KVA and the CT ratios. We'll pick up with some type of pickup value here, which will come out of the setting, and then we're actually going to increase the current until we get an operation. So here in this diagram, we're actually checking individual phase pickups, and then we're checking a three-phase, and then I'll explain this and show this later on as well. For the slope test, this is the same thing we were just talking about. Is in the slope test, we want to be able to plot some points on the slope characteristic. So when the slope characteristic is actually enabled, what we want to do is we want to test this. So we want to make sure that we put in our values for our settings into our test module, and then we want to actually pick plots across the slope characteristic and allow us to go ahead and test those points with restraint currents, and then increasing the operate until we get the percent difference on the slope characteristic setting. Okay, stator protection. So these are a couple different types. Actually, a couple. There's going to be four. So what we're doing is we're just a brief example of what these are, and then we're going to be more a little bit more concerned with the relaying aspect of it. So what we're going to do is the high impedance crown, as you can see here, is going to be connected between the neutral point and ground of the generator itself. There's going to be a step down transformer. It's going to be placed in here to allow us to get to this primary voltage here to decrease down to somewhere around 120 or 240, depending on what the transformer is going to be. And then we're also going to place a resistor across this so we can actually get the current values low enough to where we can actually apply a relay to this. We're trying to limit these fault currents somewhere around 5 to 10 amps using the different style of resistor here. The dual grounding method, this is a type that can be used with an 87 ground differential scheme. So what we're trying to do here is it's a little bit more reliable protection. Also, you can notice that you'll see a low resistive ground resistor here as well, which limits this ground to around 200 to 400 amps. But also we want to, if the ground fault is too high based upon the ground differential scheme, then what will end up happening is the ground differential, we can actually open this vacuum switch here to allow it to open, to allow this path, this fault current path, to go through our high resistance, to keep this high resistance ground path, to keep this current level very low. What we're trying to do is make sure that we keep the least amount of damage possible to the device, to the unit, because whenever we get these faults, we want to make sure that we're not damaging the equipment, so we can actually look at it, make sure we can understand what's happening, and possibly put the unit back in service once all the repairs and the proper testing has been made. On this one, we have the low impedance crown, just like we talked about in the dual ground scenario. You will have a resistor here that is actually tied to the ground. This is really common in industrial plants, not really for generation plants, but more for industrial plants that actually have their own generation, is where this will actually be used. And again, it limits it to around 200 to 400 amps. And then we also have the isolated ground, which is not grounded. We don't see a lot of these in the States, but it is out there where there's no actual tie from the generator windings to ground. Okay, so what are we actually looking for? So what we're doing is we're going to apply in the generator windings, we want to protect the actual stator winding that's in there. So in order for us to have these high impedance and low impedance grounds, low resistive grounds, we need to have some form of relay that can actually see the fault that's happening within the stator winding. So what we would place in here is possibly an overvoltage relay, usually uh, set for a value that's very low, but also we want to be able to make sure that we protect 95% of this winding. Why not 100% of the winding? Well, because the actual relay itself will only see 95%, 90 to 95% of the winding due to the voltage level that's going to happen if a fault takes place within the stator winding. As it gets close, as the fault is closer to the ground or the neutral point, then the voltage will be closer to zero. So therefore, this over voltage relay will not actually protect that area. So we would have a dead band. We'd have a dead area where we couldn't actually see any type of fault happen here. So now that we don't have, that we talked about, we have this dead band here, we actually need to use another relay, or we use another relay in lieu of this one. We also want to have it with it. So this is where we'll come into the 100% stator ground. And since the 59 GN relay that we talked about in the slide before actually has 95% coverage, we want to be able to cover the other 5%. So in order to do that, we're going to have to rely on what is inherent to the actual generator itself. So the generator actually produces third harmonics, and it's inherent in its design. And what we want to do is we want to use that. And by using that, what are we actually looking for when we're trying to apply a undervoltage third harmonic element or relay for this protection? Well, in figure A here, normal load, we would have full load. We'd have the stator winding at 0 to 100% of the winding length. And then also we would have the low load, which is, so if there's very lightly loaded, then we're still going to have some third harmonics here. Whenever we're at full load, we're going to have more third harmonics, of course, because we're actually generating more load or generating more power. But there's a little null point in here in the winding to where that harmonics, that third harmonic voltage, will be 0. It's almost like a crossover point. When you look at figure B, we're actually showing that there's going to be a ground fault that's going to occur near the generator neutral. So if there's a fault that occurs near the neutral, then all of the third harmonic voltage will be going towards the generator terminal. And then that way we'll be able to see the third harmonics going towards the generator terminal in this direction. If we have a ground fault that's actually at the generator terminal, then we will see all of the third harmonic voltage actually come down to the neutral point. So this would actually help us to cover the last 5% of the winding, of the stator winding, and then it allows to add this protection with addition to the 59N protection. So this is what this looks like. Now that we've kind of looked over a little bit of the third harmonics and what we're actually trying to do with it, we still have our 59 GN element here, and then also we have our dead band where our 59 element isn't going to look at this, and then now we have the third harmonics, which we can use as a 27 element that's tuned for third harmonics, and it's only going to look for third harmonic voltages, and it's going to pass anything that's fundamental frequency. So what we want to do is, as you saw in the previous slide, is if there's a fault towards the ground side, then we're actually going to get that relay would see the third harmonic voltage at the generator terminals. Then we have our dead band, which is actually in the middle of the actual stator winding. And then we also have, if our fault was at the generator terminals, then we would see no voltage there, and we actually see all the voltage down to the neutral side, which will allow us to use the 27N to do 100% stator ground coverage. The purpose, we kind of just went over this. The purpose of it was to be able to detect the third harmonics under voltage, allow us to get the 100% coverage using what's inherent to the generator itself. The example relays, we'll actually go through. This is a IAV, which will be a GE electromechanical overcurrent, or a CV. You know, the Westinghouse, the circuit shields as a solid state relay, and then any microprocessor based relays that have a 64G element, 2759 element. I think Basler has one out that has a 2759 element as well, paired together. What we want to do here is we just need one current and one voltage. We also just need to make sure that we're going to do the pickup 3-phase if possible. And then also we're going to do, if there's a timing element that's actually inherent to the settings, we want to make sure that we capture that as well. And then 2, we want to make sure that we do the third harmonic voltage pickup of that to make sure we are catching the 100% stator ground. If we're not doing this test at third harmonics, then we're not actually looking at that actual element. We're not in here to actually test it. So if we're not testing it, we're not looking at it, we're just bypassing it. Here's a test. Example of a test. I just kind of ran a test to kind of show you a little bit, doing a 3-phase test with an under voltage setting. I put down at about 6 volts here, and then we're testing this again at the third harmonics, which here in the States was 60. So we're actually adding the third harmonics here, lowering 1 phase down to allow us to capture that element to pick up. And there's an example of just a little test report that we have showing this test as well. Okay, loss of field. So loss of field relay, when a generator, the idea is that if, when a generator loses its stability limits and it fails to stay synced to the grid, then the loss of field protection takes over and trips the generator. But how does this actually happen? We can have loss of field or loss of excitation in multiple ways. One is the loss of AC to the exciter. If we don't have the excitation system in place, then we could actually lose excitation. So now our generator now becomes a motor. The AVR failure, which is the automatic voltage regulator failure, if that unit goes down, the mechanism breaks inside, internally malfunctions. If somebody actually leaves it on manual and doesn't allow it to regulate itself, we could get into a scenario there to where we could have a loss of field operation. We also have slip ring, flashover, or short circuit in the field. And then also the accidental tripping of a field breaker. What that can mean is if we're doing maintenance testing, we're doing any type of commissioning testing, and we accidentally trip the wrong breaker. If somebody comes out in the field and is on the wrong panel and accidentally trips the wrong breaker, we could get into a very big situation there. Field breaker latch failure. I haven't seen too many of these personally, but not to say that they're not out there, but the field breaker latch would mean that the actual breaker would just come off latch. If you have a breaker that's worn, it's had many operations on it, and you guys are still using it, it's still in the field, hasn't been well maintained, it could very well fall off latch and inadvertently trip the generator offline. Loss of field. Okay, so when the generator loses the excitation, it operates as a motor, as an induction motor actually, and then will eventually lose synchronism to the system itself. The excitation system can be reestablished, but it needs to be within a very quick amount of time. I mean, within a matter of seconds, we need to reestablish the excitation system to make sure we don't lose the generator. It doesn't fall out of synchronization to the grid. If the generator loses the excitation at full load, then it'll actually draw in VARs from the system. And what can actually happen is if this generator starts pulling in VARs from the system here, it can actually drag down the rest of the system as well. So what we want to do is we want to make sure that we give it some type of some protection parameters to allow us to just trip it offline if we are in this scenario to where we're actually losing the generator itself. We want to make sure that we're actually tripping it offline as quickly as possible. We don't want to drag down the rest of the system, and then that way we can look at what's happening to this local generator that we're having issues with and try to get it back up and back online. This is actually two diagrams. These will be two different schemes that you'll probably come across. These are IEEE recommended schemes. They're in the IEEE manual. The first scheme just kind of lets you look at, we're doing an offset mow element that looks into the machine. So this is going to have a 90-degree maximum angle of torque, and we're actually using two offset mow circles, one for zone 1 and a possible zone 2 if it is set. Sometimes you get the zone 2, sometimes you don't. It all depends on engineering. So what we're trying to do is even in the zone 2, and we'll kind of go over that here in the next slide, is pretty much our time delay zone is what we're using this one for. So we want to allow our controllers, we want to allow the plant operators to enough time to actually be able to get the loss of excitation issue resolved before we actually have to trip it offline. The second scheme here uses a negative offset mow, as you can see, with a positive offset mow for zone 2. And then we're also going to add in the directional element as well. So what the directional element is going to do is allow us to help avoid nearby faults and stable power swings and transient power swings. When we use the typical zone 1, we're just going to have a very short time delay, if any, into this zone, but we're also using our zone 2 as our main time. So we want to make sure that if our impedance comes into this zone, we want to make sure that we actually give our operators enough time to be alarmed and make sure they can try to get this resolved, or if not, watch it, because it could come into the zone, alarm, and it can also come out. So it just kind of giving everybody an idea in the control room of what's happening and to be prepared if this does have a loss of field situation happening. In the electromechanical world, there's many electromechanical relays that are used for the setup. And in the microprocessor world, of course, we only have one that can actually handle multiple elements at a time. So usually you'll have two different, when you're doing testing, a loss of field or a 40 relay, sometimes there's a couple of relays that's involved with that. And we'll have to test the timer. We'll also have to test the relay itself and make sure everything is working properly together. In this diagram, we're just going to show a little bit of the heavy load. As you can see, this heavy load, as we're out here in normal load situation, once we start getting we are in heavy load mode, we lose excitation. We're going to start this impedance locus is going to flow down here into the zone 1 pretty quickly. because we have a heavily loaded machine here. We're not going to have a lot of time as we break into zone 2 to allow the operator enough time to actually reestablish the loss of excitation issue to the generator itself. So we're probably going to trip offline pretty quickly. In the lightly loaded, if we're only using this for peaker generators or something that just has a light load as a supplemental to the system, then we can actually, it gives you a little bit more time when it breaks into the zone 2. It's actually gonna give you a little bit more time before it actually gets into the zone 1. Hopefully it doesn't, but we have to, generator protection has to take all precautions against protecting the equipment itself. So what are we going to do? Now we're going to test it. So we know what it's for. The purposes are for overheating of the rotor itself. We want to make sure loss of field, the element takes it out in enough time to prevent any damage to the generator, because it's very costly to get that repaired and we get it fixed and even get a new generator. We have some electromechanical relays. Like I was saying, you can have the old KLF is what I've been familiar with, and the CEH is out there as well, along with a timer to do for the zone 2. A lot of times it was an old TD5 or TD2 timer. Also, we have the circuit shield type 40. I haven't seen too many of those, and also the microprocessor based relays with any of the 40 elements in there will do the same type of protection for the generator package. When you do this test, it is very good to test it 3-phase. It's actually a 3-phase event that happens. So we want to make sure that we are testing it 3-phase if possible. When you get to the old electromechanical styles, they're usually open delta PTs for this, and usually one current, one CT that actually comes into this relay as well. So you're actually almost wanting to do it single phase using the 3-phase voltage. The characteristic most of the time is a Mo circle, and then also we have the MTA, which we'll see that here in a minute, how we're going to do that test. And then we want to make sure that we give it a good reach test, offset reach, and then an MTA, and at least plot a few points on the circle if possible. So the loss of field test, the MTA test, I'm sorry. What we're going to do is we're going to apply 3-phase voltage, 3-phase, and a little bit of current. We're going to get it within the zone of protection into the first zone, because we want the relay to actually pick up. And then once we pick it up, we want to swing the phase angle to either side. So we want to make sure that we can catch these two values of when we're not operating in the loss of field zone. Once we get this angle here, we will plot this angle when you'll write down this point when the actual relay opens up. So the contacts of the relay will open. We will capture this phase angle here, and then we will swing this phase angle again. The relay contacts are still being closed. We'll actually swing it until the relay contacts open again, and then that's when we'll actually see these two values, which will be angle 1 and 2, angle 1 and 2 here, and we will take those and divide by 2, and will give us our maximum torque angle. So for the reach test, we're still using the Mo circle here. That is actually from the settings. We'll apply settings in the program for the test plan. We'll actually apply the settings that we need, and we'll put it into the test. We'll create the, if you can, test with nominal voltage. If that's not a possibility, sometimes you have to decrease the voltage. Sometimes you have to just kind of mess with it just a little bit so you can get it within the zone of protection. And then we want to increase the current until the impedance operates, right? So we want to pick some points that we would like to test in our reach test to make sure that we are validating that our impedance circle is correct, the diameter of the circle is correct, and we get a couple of points on here to validate the settings from the engineering department. The offset test is the same as a reach test. We're just testing the top of the circle. Again, in order to get this, you're going to have to decrease your voltage a little bit. You want to make sure that you are able to plot this point here, and if you want to plot a couple points, you can put a couple points on the edge. You can't really test a circle with 1 point or 2. 3 points minimum to actually prove a circle. So it's nice to at least have 3 points. Inadvertent energization is another element we're going to go over. So inadvertent energization is protection that we use to limit the damage to the generator in case we accidentally energize it. So if the generator is on turning gear, or if the generator is ramping up to be synced to the grid but hasn't really been synced yet, and we accidentally close the breaker in with the frequency not up to system frequency, that could be an inadvertent energization situation. That's a lot of words there. So what it seems to be a big industry-wide problem that it warranted its own protection scheme, and has been set in the IEEE standards as well, that we actually need to protect against a standstill generation, and then we're using a combination of an overcurrent and an undervoltage relay to sense this type of issue. So the ways that this can actually happen is, well, I just told you how they're going to happen. How about that? So what I was going to say is the conventional protection. Why can we not use something else besides the 50 and the 27 element? Well, it operates. It won't operate in a timely manner in order for us to catch it. So the element won't actually catch it quick enough to cause the least amount of damage to the actual rotor, to the stator, to the unit, to the turbine blades. And to the distance relays, if you're looking at distance, a lot of times those are disabled during maintenance and during shutdown. So when the generator's on turning gear, most of the protection is disabled because the crews are out doing maintenance on substation. They're doing maintenance on all their protective devices out in the yard, and so a lot of times this stuff gets disabled. And then two, it's not really that sensitive to catch. It's hard to catch this if you don't have a specific type of protection or some type of scheme put into place to look for it. So what are we protecting against? We're protecting against a machine when it's not spinning or on turning gear, or operator or breaker flashover. So the breaker flashover would be is when, like I was saying, when the generator is actually moving up to speed, and the breaker poles inside the generator breaker actually flash over due to an insulation breakdown inside the breaker itself. Could accidentally energize the generator itself while it's getting up to speed. Relays, this is the one that Bachelor's come out with. It's actually a 5027 relay specific for this application. And then also, any microprocessor relay that's putting two elements together in logic, or actually has its own specified relay element for this. And then what are we going to do? We're actually just going to validate the scheme. We're actually going to sit here and we're going to do a supervised overcurrent test. And some I haven't really seen personally, but the frequency, to be frequency supervised, I have not been involved with that, but there are the voltage supervisions are the most common. And it can be tested using three-phase or single phase, and we are going to test the instantaneous overcurrent element, and then we're going to verify a time delay, of course, if there is one. So this is just an example of a test that I ran on the energization portion. I just gave it some type of instantaneous overcurrent value here, and then also a under voltage element to allow this test to happen. And I'm just running a quick time test for this. Not saying that this thing is 1.1 seconds out there. It's just something that I just ran in a simulation to kind of show what the actual test would look like once we actually get to this element. Okay, reverse power. Okay, so the primary indication of motoring is the flow of real power into the generator, and it's acting as a synchronous motor. When we lose excitation, we're actually going to see the generator is now not generating power, it's not producing power, now it's absorbing power. So it's bringing power in from the system. When you see here, you would have forward power flow, and then also we have reverse power flow. So what we do is there'll be a setup pickup point that'll usually be set in watts with the combination of current and voltage. And what we're going to do is there'll be a pickup threshold here, and as long as we're not generating past this threshold, we will not trip on reverse power. Now this usually happens pretty quickly because it's going to be a race between the loss excitation and the reverse power relay. So it's kind of, if we're in zone 2 of excitation, of loss of field, loss excitation, then we could actually, that time delay could be long enough to where this guy would the impedance would actually swing over and we would be in to reverse power. Because it's just kind of a race. I've seen multiple times when a generator's tripped offline and you get two indications and you're trying to figure out which one actually happened. Most of the time, if your generator if you're running your generator and you trip offline and you come back to it, most of the time you will see a reverse power target on the relay itself. And then the purpose of all protections, you have some type of trip and alarm, because you want to go into an alarm state as well to make sure that people are actually seeing it before it actually happens, so we can try to resolve the issue. The element is three-phase power, so it can be tested single phase, as you can see here, and then most of the time the relays will calculate it into three-phase power. And then it's pretty easy to test. So what we're monitoring the generator to detect the power failure. We can also see in the diagram again here, there can also be a 32, which would be for power. We can also see that there might be a forward power element that could come into here as well, which would be low power. So as we're starting to get into the reverse power condition, we could also have a set point that would be set here for forward power. So it'd be a 32F. What types of relays? We got a GE, electromechanical style relay, GGP is pretty common. The ABB CRN relay, circuit shield, and then also the microprocessor, any microprocessor relay with 32 elements, 32F, 32A, F, or 32R. It can be tested with single phase current voltage. As for the electromechanical relays, you can test that way. For the three-phase, if you're doing a GGP or a microprocessor relay, it's a lot easier to test using three-phase. It makes the test easier to configure, and also you can just calculate it in 3-phase just like it's actually going to be in the system as well. So anything that we can get as close to testing like it is in the system, the better we are. We try, some electromechanical worlds, they only allow you to test in a certain manner. What we do try to do is, if possible, test how it's actually hooked up into the system. Test using nominal voltage, and then of course the current's going to be fairly low for that element as well, and then we're also going to give an alarm or a trip. Here's an idea how to test it. So what we're doing, just a simple 3-phase test. We come in with nominal voltage, doing it your forward direction on the voltage, and then we can change the current values, so 180 out, and get to the watt setting. So we would actually have to take that watt setting and then calculate it using the voltage that we're going to actually use for our test. Will give us our current value that we're actually going to apply for the test itself. And then we're just going to reverse that current as far as the phase angles, bring everybody 180 out, as you can see in the diagram here. All right, fun stuff. All right, so we have RTMS, which is our relay test management software, and is a tool that we have with our test equipment. We can provide a way to quickly set up these elements, as you've seen through each one of the slides. I've actually had a test example on the end of each one. It's real simple, real easy to use. Wait, was I off slide? Yeah, it was. Okay. All right, so what I like to do is just kind of show a quick way to set up differential testing. So if we're going to test a generator differential relay, these are the elements that we're going to go over, that like we talked about earlier. This is the setting template. The setting template actually has a way for us to input the setting values. And again, we're getting these values from the settings. Nothing in here is come up any extra. We do follow everything from the manufacturer's guidelines. We have a few drop-down lists for different manufacturers, but also most of this information gets put in from the settings. So you shouldn't have to go hunt this information down. You should be able to get everything that you want to fill this sheet out with from the settings by pulling them from the relay, or if you have electromechanical relay that's 3-phase, you can pull those settings from that relay itself. I don't see a lot of electromechanical relays being used with this test template. Most of these are going to be used with microprocessor based relays, since we will be injecting 3-phase current, and so it would actually take 3-phase from the winding 1 and winding 2. I almost wanted to hit the check mark up there. Thought I was in the test mode. Yeah, so this is the connection diagram, so it kind of gives you an idea of what we're looking at. So when in a microprocessor relay, we're actually going to be hooking up on primary winding all 3 phases, and then we're also going to use the secondary winding for all 3 phases as well, because we want to produce the test that's in just how it's set in the system. We don't want to change it if at all possible. Again, some relays you just can't help that, but most of the time we do want to test everything as it's built and wired in the system. Something's going on with my mouse here. Okay. One of the tests we are going to run is a stabilization test, or what is also known as through fault current test. And the reason why we want to run this test is there any value in it? There's absolutely, there's a lot of value in this test. One is we want to make sure that the relay is not going to trip during through fault situation. Also, we want to make sure that our test leads are correct. We want to make sure that our test leads are connected properly, and this is a good check to determine if it is or not. Do we have a faulty lead, a test lead going to the relay itself? Do we have bad connection? And this actually will prove it for us here. What we'll do is we'll inject these values, secondary values, of course, into the relay itself, and then on this side, will be the user, or the technician will actually apply these settings into this field from the relay itself. And then that will give us a good true comparison of what we're putting in is what we're getting out. That will validate our connections, that will validate our leads are proper, that will validate that we have good equipment and everything is working properly. So it is a good test to run. It's always a good test to run at the very beginning as well. We'll do our pickup test. So the pickup test itself, the pickup test, we're going to do a pickup on each individual winding. This is very similar picture what I showed before in the differential section. So the pickup values we're doing in per unit here according to the setting template. So we had the setting template up in the first. Those settings are what we're basing our test values against. So we will increase the value until the relay operates, and then we'll actually get a result depending upon our percent error that is set by engineering, your plant, your firm, however you want to do it. But those guidelines we can set in here. The slope test, again, like we went over it before, we'll do it again, is the restraint and operate. We're actually holding a restraint value here, and then we're actually increasing the operate current to make sure we're in tolerance of the percent slope. And these, on this particular software program, you can just select these dots. You can just click on this actual slope, and we'll actually populate these points for you. So it's very easy, very user-friendly to set it up using RTMS software. And again, at the end of the day, what are we looking for? We're looking for test results, right? So this is actual proof that you were there. This is actual proof aside of you taking a selfie and putting your face up here in the logo. It's the only proof that you have that you are actually on site doing testing, and you actually got a valid result, and everything is good for the end of the day. Your testing company, this is basically your paycheck. This is how you get paid. And for normal utility and everybody else in the world, this is validation to government entities, to management and so forth, that this is actually the test that you ran, and it also gives you some type of data to track and trend your equipment. Okay, so in the summary, there's just a few takeaways. So what we want to do is we want to make sure that we learn the relays and we learn the protective elements in those relays, so we're allowed to makes us better to test. We need to know what's happening so we can test it. We need to get familiar with the test equipment and the software. We definitely don't want to run out there on day one unzipping everything out of the plastic and ripping it out of the bags and installing drivers and installing software, and we're sitting in front of a relay panel as day one, getting ready to learn on location. We need to be familiar with our test equipment before we even go out in the field. We also want to adhere to a standard way of testing. So if you are using NETA's MTS spec, if you're using IEEE, if you have your PSMP from your utility, the utility for NERC standards, the PSMP will be your guidelines that you can request. As a testing company, you would have to request this information from the utility to allow you to test, follow the same pattern of testing, which keeps you in a standard way from the next guy that was there before you, and then the ones that are following after you. Follow the testing practices when it comes to relay settings. Pull before you get to the relays. If you have electromechanical relays, we all have phones. Take a picture, write it down, whatever it takes for you to remember what the settings are, and before you touch the relay. So if you have to take a picture of it, if you have to write it down before you pull it out of the panel, great. If you are doing some type of microprocessor-based relay or something that has software to it, then pull those settings out as found. Pull those settings out, keep those settings on your PC or close to you, and then that way whenever you get done testing, you can put those settings back in a relay and run a compare function. You want to make sure that you always compare the relay before you walk off, because you're the actual last one to ever touch it, and those fingers get pointed at you if something happens. And also, it's just kind of a little bit of knowing the scheme. Know the scheme in which your protection, what you're testing. If you don't really understand what you're testing, then maybe it's very difficult for you to know the right and wrong from the relay test reports. If you're just going out there just running a few tests and just handing in the document, and you were already there, and then somebody else is overlooking you because you didn't really understand what you were testing, then you have to go back out there. That's more time, money, and two, it just saves you a headache from having to go talk to the big boss about why you have to go back out in the field. So, you know, just know the scheme. Just do some reading. There's lots of information online. There's lots of information. If you guys have questions, you can always call us. We have lots of information, lots of resources to help you out. Okay, it's just a little area of some references I used. So today we talked a little bit about the RTMS testing. Also, we have multiple pieces of test equipment that can perform this testing. We have our three-phase units and single-phase unit. We have units with displays, units without displays, units that can be used with this PCs. All these units can be used with a PC, and we're all driving it using the same RTMS software. So if you guys have any questions, definitely let us know. We'd like to come out and show this product to you. We would like to sit down, do a little bit of examples and testing, and kind of helping you get familiar with the test, with the software. If you already own a piece of equipment and you just have a few questions about doing some of the testing, then let us know. We don't know if you don't let us know. So please give us a call in, let us help you out, let us walk you through some of the scenarios and through some of the tests, and that way it just makes everybody, we're all learning, we're all going through, and the products are really simple and easy to use. Okay, I think Mr. Mike.
Thanks, David. At this time, the presentation portion of the webinar is officially concluded. We'll take about 30 minutes to answer as many questions as possible. If you have any more questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you would take a couple minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of the presentation, along with a link to the video recording and a link to your video recording of the webinar will be emailed to everyone in about a week. You can also view the recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, Best Field Practices for Testing Instrument Transformers, CTs, VTs, and CVTs. The presenter will be Daniel Carreño, Application Engineer. So let's get to your questions. Our first one will be directed towards Abel. The first question is it okay to have third harmonics coming out of a generator?
Hi, well, good morning, everybody. The generation of harmonics out of a generator is something that it's a consequence of the lack of linearity of the flux in the air gap. So I guess what I'm trying to say here is that generators do generate harmonics. Third harmonics in particular are generated and available at the output of most synchronous generators, except when design and manufacturing steps have been taken to prevent the generation of those third harmonics. You can fight some of the harmonics, but you cannot fight all of them because of the, like I said, non-linearity of the flux in the air gap of the generator. However, to answer the question now, is it okay to have them coming out of the generator? I would say it's not a matter of okay or not. It's a consequence of physics. Now, the generator step-up transformer, being a delta connected delta star connected transformer, takes care of those third harmonics and insulates the generator from the influence of third harmonics coming from the system and insulates the system from the influence of third harmonics going out from the generator.
All right, thanks. Our next question is going to be directed at Danibal. In 32 element, which one will operate the relay? Only current in reverse direction or voltage?
Hi, good morning all. In general, 32 element is used to product the prime mover loss power. So when we are in synchronized condition, prime mover started losing the power. Basically, it's not able to pull at the speed. Then generator started drawing the current from the system. So basically, the question, the answer for this question is it's the current. We reverse direction of the current and we calculate the reverse power to product the element.
Thanks. Next, we have a comment that I think you might want to follow up with. The comment is, I've seen reverse power used on a controlled shutdown to protect the unit from overspeed. To validate that the top valves have actually closed and removed the power from the prime mover before opening the generator breaker.
Yeah, I'd like to comment on this one. It is not the usual practice, but some of the utilities do on the controlled scenarios. It is sometimes it is risky to stop valve to stop the valve's prime mover power completely, then stop the generator power, basically setting up the excitation power. Sometimes it is over excite. Also, it is possibility it can go into the capacity mode. Basically, it's called troop mode. So that's risk for generator, but very well controlled and very knowledgeable, well-trained people can do this process.
Thanks. Abel, we have a question for you. Can we do differential testing with two different CT ratios?
Well, you can do any differential testing with any CT ratio, I would say. The generators, however, are not the type of units that you would connect with different CT ratios because of the fact that you have essentially the same current going from one end of the winding and the other end of the winding, you have essentially the same current going in series. But the answer to the question is yes, you can do differential testing with two different CT ratios.
All right, thanks. Real quick, we have a question coming in. How do we get the PDH for this webinar? That will be included on the email coming out in the next 2 business days with a copy of the PowerPoint and the recording of the webinar. So keep an eye out for that. Our next question for Danibal is, what is the best way to test the 87 ground differential function to ensure the wiring and CT polarities are correct?
Yeah, it's a really good question. Every production and commissioning engineers will face these issues to make sure 87 differential is working fine, because it's really difficult to test on the secondary injection. So we have 2 possibilities to test this. One is like during pre-commissioning, like SEC test, you can able to verify it, or even or just inject the voltage in the not in the SEC test. Just inject the voltage from the, like you got a GSU, HV side of the GSU, like your 3-phase supply, inject and short circuit the secondary, and you can be able to see the, it may be very less current generated based on the reactance impedance of the generator and this stator circuits, but still you can able to see the current flowing into the circuit and able to check the CT polarities.
All right, thanks. There won't be a poll question for this, for those who just asked. Our next question is going to be for David. Hopefully you had a nice rest. The first question for you is, how do you do slope 2 testing with RTMS?
So it was a little difficult to see in our slope setting, or the actual slope test itself. And in there's actually a line for the minimum minimum differential setting for then there was a slope 1 and a slope 2. So the gradual slope that you saw, the biggest slope on the screen actually was actually slope 2. Slope 1 was in that first area where I was getting into, where the first set of points were at. So there is a little breakover in there. It was very small, but that was also dependent upon what settings I had in there at that point in time. But you can go into RTMS and actually set the slope 2 setting. All it is setting the slope values into the setting template screen, and then going in there and then selecting on the graph where that test point is that you want to test for slope 1 and slope 2. So it's in there. It's just on the screen. It was a little difficult to see during the presentation.
Thanks. Next question is for Danabal. Why do we need to apply third harmonic voltage to test 32 protection?
It is not usual. We use third harmonic for 32 element because 32 element is applying fundamental frequency operation. Normally, we use the third harmonic for the ground elements like 95% element or 0 to 100% elements, not on the 32 protection.
All right, excellent. Next question is for David. 81 element was not mentioned. Is that something that is changing or has changed?
No, it hasn't changed. I didn't mention it in here. Like I was saying at the beginning, there's in my what is that? The outline for the generator protection. There's so many elements, and for an hour webinar, it's very difficult to get to every one of those. We had to break this up into multiple pieces. So, you know, you just kind of pick what elements that you want to talk about this time. The next time we pick something different with maybe the under and over frequency, and then we'll do out of step, you know. So it's still there. It's still relevant. It's still in the system. It's just, I didn't talk about it this time just due to time. You can almost make a whole day out of this just for doing all the elements out of here.
Thank you. Next question is for Danabal. On what loading points should measured third harmonic for stator ground relay set points?
Yeah, third harmonic measurement in general, even including IEEE standards, like we measure on the 100%, is basically 1 per unit of the generator capacity. So say example in 100 megawatt generator, it may be like close to 5 to 6 voltage third harmonic generation happen.
All right, thank you. And our next question is for David. I still use my AVO Pulsar. Where do I get support on the AVTS software?
You're using the AVO Pulsar. We do have a good trade-in program for that baby. But also, you are still using that. It's amazing that it's still working because you must have got a really good one, or you got a lot of spare parts. The AVTS software you can get on Megger website, and I think the last version that we do have available is 4.3. We no longer are supporting that software, but as far as updates, but if you want to call in, you have a question about test plan or something that you're trying to work through or create, or running a test or trying to connect to it, you can call us and we can still help you support your questions through the AVTS software. So the only thing we're not doing is just putting out any more updates for it, but we're still supporting the AVTS software. So you can definitely call in to our Megger TSG. The information was a couple slides back. Just call in and we can help you do whatever you need to do with it.
All right, excellent. Thank you. And then our next question is for Abel. How can we test rotor first and second ground faults?
Can you specify the question a little bit more?
Yeah, we have Danabal here.
Abel, I can take this one. Yep.
Okay.
First thing on the rotor ground fault, we have a different methods to product rotor, like impedance schemes, like controlled impedance scheme and the injection principle. In case of injection principle, it's pretty straightforward. Just you can in the generator offline, you can make the ground anywhere, then it will work. on the first and second ground fault happens in the real controlled impedance mode. Just like you can touch the brush to ground at one side and in the running condition, not the generating condition, but it's running condition, you can see the ground impedance changes. Then normally the first ground fault on the rotor is alarm. So then we make the another brush or other ground terminal on the ground side. We touch, then it will make the second ground fault, and second ground fault usually it is the trip for the, it's a unit production trip, basically to isolate everything.
All right, thanks a lot, Hannibal.
Sure.
It looks like we're out of questions. If you think of anything else at this point, just feel free to contact us offline. Thank you all for attending. If you could please remember to answer the survey at the end of this. It'll include a field for you to request a demo if you're interested, and let us know how David did. Thank you all again for attending, and have a great weekend.